Imagine sitting in your clinic when a frustrated parent slides a highlighted printout across your desk, claiming a new study contradicts everything you've recommended. Clinical mastery extends beyond physical observation. An international board-certified lactation consultant, or IBCLC, must decode scientific literature to distinguish verifiable facts from statistical noise. Medical research is organized into a hierarchy of evidence. Think of it like a courtroom trial. Just as a judge weighs hearsay differently than hard physical evidence, researchers rank study types from weak circumstantial observations at the bottom to definitive proof at the peak. Evaluating clinical research requires understanding the specific statistical language used at each level of this hierarchy, from basic qualitative patterns to complex quantitative data. The quality of the underlying evidence dictates our clinical confidence. We have to evaluate a study's rank to know if its conclusions are actually trustworthy enough to guide patient care. At the bottom of the pyramid, we find expert opinion, case reports, and cross-sectional studies. In our courtroom, this is the equivalent of hearsay or a single eyewitness. It represents a single isolated data point at one moment in time. These lower tiers often rely on qualitative data, like words and patterns gathered from focus groups. While this is helpful for showing basic associations between two things, it cannot prove that one thing actually caused the other. Moving up to level 2, we reach observational studies. Here, researchers look at larger populations, splitting our timeline into two directions. Case control studies look backward at past exposures, while cohort studies look forward to track outcomes over time. Case control studies express findings using an odds ratio, or OR, which calculates the relative likelihood of an event. For example, an odds ratio of 2 means the outcome is twice as likely to occur in the exposed group. Cohort studies use relative risk and rely heavily on confidence intervals. A confidence interval is a bracketed target range within which the true effect is likely to fall 95% of the time, establishing the study's margin of error. Observational studies can reveal strong circumstantial patterns, but because researchers cannot fully control the subject's environments, these studies still fall short of proving absolute cause and effect. Level 3 introduces Randomized Controlled Trials, or RCTs. This is the undercover sting operation of science. By randomly assigning participants into an intervention group and a control group, researchers actively eliminate bias. In an RCT, researchers actively manipulate the independent variable, like giving one group one-on-one lactation teaching, to measure its direct effect on the dependent variable, such as the resulting levels of maternal attachment. To ensure their results aren't a fluke, researchers calculate the p-value, which is the exact probability that a finding is due to chance. Tipping the scales with a p-value of less than 0.05 proves the findings are statistically significant, meaning there is less than a 5% chance the results occurred randomly. By controlling the variables and achieving statistical significance, randomized controlled trials cross the critical threshold from showing a mere association to proving definitive causation. At the very peak of the pyramid sits systematic reviews and meta-analyses. This is the supreme court of research. Meta-analyses aggregate all previous high-quality RCT evidence and merge it into one definitive global ruling. This chart shows a forest plot, which is the standard visual tool used in meta-analyses to map out data. The point estimates are represented by black boxes, and the size of each box corresponds directly to the study's sample size. A larger box means more participants and greater weight in the analysis. The horizontal lines extending from those boxes represent the 95% confidence interval. If a study's horizontal line crosses the central vertical axis, known as the null effect line, it means the true effect could be 0, and the study is not statistically significant. Before accepting this aggregated data, researchers must check the I-squared statistic. This measures heterogeneity, which is the percentage of variation across the individual studies that is due to actual differences rather than random chance. An I-squared of less than 25% means low heterogeneity, indicating consistent gold standard data. But if the value is over 50%, it indicates high heterogeneity, warning us that the underlying studies are messy and conflicting. Meta-analyses provide the strongest quantitative proof, but we can only trust that final ruling if the underlying studies are homogeneous and methodologically robust. Transitioning from the math back to the clinic reveals a final trap for IBCLCs interpreting research. Just because a study achieves statistical significance does not mean it has clinical significance. This graphic compares a dramatic relative measure on the left to an absolute measure on the right. A study might report a 50% relative drop in a particular risk. However, if the baseline risk was only 0.8% to begin with, that relative drop translates to a 0.4% absolute risk reduction in the real world. A tiny absolute risk reduction might come with a perfect p-value, but a 0.4% difference is practically meaningless for the mother sitting in your clinic seeking actionable help. Mastering the hierarchy of evidence empowers you to filter out statistical noise and spot hidden biases. By understanding how to read the data, you ensure that you deliver only the highest quality, most clinically relevant care to breastfeeding families.